And magnetization is not even saturating until the 60 Tesla, up to the 60 Tesla. And if you look at the C-axis, it's even worse because it is, you can see the difference is a factor of 3. And one may think that there might be a G factor, which plays the role here, but G factor is free electron is 2. Difference between the AB plane and C-axis, this is a factor of 3, is almost impossible to think because you need some kind of distortion and Spinover coupling to get the G factor to be different. And the distortion is small, like a trigonal distortion or monoclinic distortion is a perturbation to the dominant Kitaev and gamma interaction. So we do know that they are very tiny. So you can get the G factor of this much a difference. So in that time, during that time, we know that this strong anisotropy is in fact an indication that the gamma interaction is large, not that small. And also it has to have a sign of antiferromagnet. And the reason for that is because if you write this Curie-Weiss terms in an ABC coordinate, remember this comes with XYZ. XYZ is a local coordinate, while ABC is a crystal axis. If you write in an ABC crystal axis, gamma interaction comes as the antiferromagnetic along the C-axis, while it comes like a ferro. There is a minus sign change, comes in the AB plane. So if you apply the field, this one is going to compete with the Zeeman interaction along the C-axis, and that gives us pretty different anisotropy, and it's hard to saturate the magnetic moment because of these gamma interactions. So that was kind of identified. Now, the magnetic field studies is lots of them, lots and lots. After that, there is 2016. I have listed only few of it. It's mainly earlier days. There is many of these papers are very, very nice. And there are some debate over whether the after Zig Zag is destroyed, do we get the Kitaev spin liquid or non-abelian anions that pops up, or is it polarized? Many of debate here. Even in the independent from the ruthenium trichloride, there was suggestion that if you look at the, for example, this Kieran and Simon Trevest, if you look at antiferro Kitaev and if you apply the field, you end up with some intermediate state which a yuan spin liquid before it polarizes. So some of those excitement came out, some of these papers along that lines. And then after that, there are many others. So I won't be able to cover definitely all of it, but I'm gonna touch just a couple of them. So neutron scattering, this is a recent data under the magnetic field. If you look at, so let me try to remove this screen here because it's kind of bothering me. So this was in plane magnetic field along the A-axis. A-axis is the one, it's in plane that is perpendicular to the bond, the honeycomb bond, one of the honeycomb bond. So let's look at here. If you look at this, is a spin wave with a 00L is along the C-axis, and one can see that this is a low temperature data. One is a 0 Tesla and the other is a 13.5 Tesla. You can see a nice spin wave dispersing along the L. And if one follows both of them, let's say at 0 Tesla, which is this one and that one, and they have plotted only two. One is the top one here, which is going to correspond to, in fact, that they use the difference. So top one is going to be this spin wave peak here, and then bottom one will correspond to this one in here. And then they apply the field, and the high field of the 13.5 will correspond somewhere here. You still have this nice spin wave where the energy is going up here, and then low branches is also dispersing and go up here. And notice that this is the 0 Tesla and high field. So 0 Tesla and high field here. In the middle, the spin wave disappears and then it comes back. It's basically, there is a nice spin wave, it's falling, and then there's a big error bars here. Something is happening in the middle, which is about window of the 2 or 2.5 Tesla. And then there is a magnetic wave that pops up. So you know that something is interesting going on. And they also have done the series of other experimental proof, which is magnetocaloric effect. And then this is this DC susceptibility and neutron deflections. INS is inelastic neutron scattering, CP is the specific heat. So all of this data is kind of telling us that in the middle in here, in addition to two different zigzag orders, these are two magnetic orders, there's some intermediate phase that appears before it polarizes, meaning it's all aligned, field directions, it's continuously connected to the direct product state of the classical state. So something is going on here, and that's where the thermal hole, which was even earlier than the neutrons, was found that there is a half quantized thermal hole conductivity. So here is the kappa xy over the t, that's the absolute quantity number here. But if you divide into the unit of the kappa xy d divided by t, that's a pi by 6 with a kV squared divided by h bar. And that's a half quantized, which was found within this temperature here up to around 6 Kelvin. And that's the temperature range. And this is a field range. So within a field of 1 or 2 Tesla, they do find some half quantized thermal hole conductivity. And this was a kind of big thing. All right, I'm trying to check if there's any raised hands here or anything. Okay, good. So after that, many of people were surprised. The community was excited, but at the same time was like checking like, okay, there must be a other way to measure this, or is there any other groups which will reproduce this? And this is still waiting. In the meantime, there has been other proposals, for example, this thermal hole conductivity was obtained if you have this Kitaev interaction, pure Kitaev, and the magnetic field, the Zeeman, you can take a perturbative approach in such a way. If you put the direct Zeeman here, this is no longer solvable. So what Kitaev did was that you can write in such a way that it's remained to be exactly solvable. So you can expand the Zeeman terms, and the first expansion terms are 3 spin terms, and that's still exactly solvable. And what one can show is that there can be a transition between the two of this non-abelian anion state, depending on the direction of the field. For example, as I said, if you apply the field, in this case, out of the slide, you will have anti-clockwise Majorana fermions, which are moving along the boundary. But if I change the direction of the field, you will get a clockwise. So that is represented by this sum number, which will change the sign. One case is 1 and the other case -1. This transition has to be obtained through the Majorana gap closing and opening. So this is a topological transition, just like a topological insulators, where you can change the sum number only through some kind of transition. So half quantized thermal hole, in fact, has to change the sign depending on the direction of the field. And that's exactly what they say in 2000 here. So sign change of thermal hole was found. So here, what they've done, they changed the in-plane direction of field. So as I said, this direction here, perpendicular to the bond, is an a-axis. Parallel to this bond is a b-axis. And what they have found is that when they have a field along the a-axis, along this direction, they have positive here. When they put the in-plane field along the b-axis, it becomes a 0. Here is the 0. And then, and this is just a temperature dependent. So you can see that here is a low temperature, and then kappa xy in temperature is rather, I found it's rather something that we should note, is it goes up. So in some sense, quantization is very, very tiny. You have to work it hard to see it. So, and it's grows up here and then comes back, and of course it goes to around 0 as expected. So b-axis is 0. And what they have seen it is that if they rotate, for example, field along this axis and then rotate from -60 along this direction and +60 along that direction, you can see that the quantize half change the sign. Like here's a half and there's a -half. And if you zoom in, this sign here is quantized between 9 to or 10 to something like 11 to 12. Or 10.5 to 11.5, something like that. and -half is also found around the same field range, and then it goes away. So that was the sign change of thermal Hall. This was, I found, as a strong signature of the field-induced Ising topological order. And that's hard to explain. So let's go back to the microscopic model that we have discussed in the first lecture. So to understand the field-induced intermediate phase, remember that if we're starting from the spin model, we can get the Kitaev interaction, which dominate all of this. That can come with the different signs that can be antiferro and ferromagnetic. If the intermediate, the indirect hopping through the oxygen, well, in this case, the chlorine p orbitals is dominant, and this will be a ferromagnetic Kitaev. And next, the largest term will be a gamma interactions, which we expect it to be antiferromagnetic through the sign of those hopping terms. And then there's a Heisenberg interaction. This one is coming from the trigonal distortion, so we expect it to be small. And third neighbor, Heisenberg interaction, monoclinic, and then we add a Zeeman term. So you can see that this is a huge phase space, and where to look for intermediate field-induced state becomes rather challenging. And we believe that here the ruthenium trichloride 3 is sitting somewhere in this areas where in this areas where Kitaev interaction is ferromagnetic and gamma is most likely antiferromagnetic. And if you add a small trigonal distortion, one can stabilize around this area to be a zigzag, and one can destroy it using the magnetic field. So that's the scenario. However, can we really get the intermediate phase? And that intermediate phase can just not have to be in the just intermediate phase, but it has to be Kitaev spin liquid with the field. So it sounds rather difficult. So let's go to see if we can, where we can start. All right, so if I have been looking for some list of the proposed parameter sets, and this is the one of the most updated one. It's in the Shasha Sherenikov's one in the archive. You can see that how many people, I mean, these are only a partial list. Most of these are ours, and some are coming from other people. Kitaev interactions are mainly ferromagnetic. Gamma is, some are the ab initio, some are fitting into the data such as neutron sketchings and so on and so forth. And gamma interaction is antiferromagnetic. And this interaction is ferromagnetic. Heisenberg is a small ferromagnet. So all of this are kind of speaking the same range of the parameter space. Recently, the other one that I want to comment is that if you look at the magnetic moment, that magnetic moment also tell you about the some sign of the, at least the dominant terms. So this is Jennifer Sears, Youngjun's former student at Toronto. They have done the resonant inelastic, well, RIX is a resonant inelastic X-ray scattering, but this one is a resonant elastic X-ray scattering. And what they have, doing those, they can find what is the magnetic moment in the zigzag state. So this is inside the zigzag order state, low temperature, no magnetic field. They do the REX and see where is the magnetic moment point. So, and they have found that, so remember that XYZ is a local coordinate determined by the octahedra. So here's an X direction, here's a Y direction, here's a Z axis, which are set by the chlorine here. On the other hand, the crystal is aligned in such a way that AB plane is sitting in this plane here, and then this is the C axis. So C axis is pointing center. You can see this triangle here. So if I go along the center of ruthenium to point, moving along here and then passing through the center of this triangle is going to be a C axis. So this plane is written in the AC plane. I have copied from this Kitaev's paper here. So that's going to be C-axis. This is AC plane. And what they have shown is that if the Kitaev interaction is antiferromagnetic, then you can tell the moment, in fact, has to point along the Z-axis. On the other hand, if the Kitaev interaction is ferromagnetic, then moment has to plane in this XY plane here. It's a classically degenerate, but if you add a quantum fluctuation, it'll point in the cubic axis, which is either X or Y axis. Then what they have further shown is that if the gamma interaction is negative, then it will start from this cubic axis, which is X, and then it will rotate towards this axis, which is the far away from this coordinate. On the other hand, if gamma is positive, which is the antiferromagnetic, it will rotate towards opposite direction, which is sitting in the somewhere in between the XY. And then if it is large enough, then it'll further go away from this axis, but it is staying in the AC plane. It deviates from this XY planes. On the other hand, in the antiferro Kitaev, if gamma is a plus or negative, it'll change between these two directions. But you can see that how the arrows are represented. It doesn't change much. And that's because antiferro Kitaev is much more robust. And if you compare with this analysis with the magnetic moment direction, it's exactly sitting in this point, which is the moment is sitting along somewhere here. So one can tell that gamma interaction has been kind of large. It's as big as the Kitaev. So that's ferromagnetic Kitaev, antiferromagnetic gamma. And one, as I told you, the G factor is also has to be kind of unreasonably large to explain such a phenomena. So together with the susceptibility, we are kind of confident where we are in terms of the material parameters. And this is also the moment here, as I showed you last time in the first lecture, this is also consistent with this Hung-Sik's paper that has shown back then that the moment is pointing along this direction using the ferromagnetic Kitaev and the antiferro gammas. So the question is then, goes to, okay, we know that most likely that many of experiment is telling us that the largest interaction is ferro-Kitaev and antiferro-gammas, and then we put the field. Then okay, then what do we do? So this putting us in a difficult position because as someone asked in the last lecture, you're dealing with a 24 site ED, and this is going to be very tiny. So if you have a large unit cell magnetic order, if you have incommensurate orders, then how you can tell, because then all of this might be something to do with the finite size. So I was thinking maybe one can get some guide from the quasi-1D system. In other words, if I starting from chain or ladder where numerically I can access much bigger system, despite the geometry is confined in the ladder, but I know that if I have found the magnetic order in quasi-1D, which is accessible by numerical method in a much bigger system. For example, if I have a ladder like this one's here, I can make the system size like a 400 site, which is accessible by the OBC, open boundary condition with the DMLG, or I can do the IDMLG in a much, much better way. And if I do find the order state in this quasi-1D system, in this case, because one-dimensional system has much more fluctuations, likely that in 2D system, those phase space are out of pictures because those areas will likely have some kind of magnetic order, especially some missed incommensurate order due to the finite size 2D cluster, like a 24-site honeycomb cluster may miss some incommensurate order, and we may be able to find those ones in the small confined geometry. And it's interesting to note that Kitaev chain and ladder, those has been studied quite early, back in 2007 here, and it's exactly solvable again. One can show that this is the chain. One can describe this as a Jordan-Wigner transformation. It's free fermions. You can put a ladder here. The way the ladder is put is that this is a honeycomb, and because I only have two chains here, this G bond here, this G bond is combined with that point here. So you form a kind of scale ladders here. So this is X bond, this is Y bond, this is Y bond, this is X bond, and then there's a Z bond, Z bond. So every point has the X, Y, Z. So it has the geometry of the three coming out the XYZ Kitaev point. And what was shown is that in the ladder here, this is the just like AB. What's that? In the Kitaev. Remember that there is in the center here when they're isotropic. This is the draw, rather differently. So this is the JX over JZ. This is JY over the JZ. So isotropic point is this circle here. So inside here is going to be a gapless Majorana extensions, which is the Kitaev called the B phase. And every other corner here is going to correspond to this A phase, AX and AY, AZ. And those are the tori code where abelian anions was found. So one can get this from the chain and then ladder. And then this is 4 chains, 6 chains, and 8 chains. You can see that what happens is that in the ladder, this isotropic point is actually gapped rather than gapless here. So this is a 2D limit, and this is a ladder limit. It's gapped. It's gapped. However, this boundary where the B phase and A phase occurs, at least here, AX and AY, this boundary where the tori code and gapless Majorana extension occurs, this boundary is captured in the ladder. So ladder here, just even 2 chains, is able to capture this inside phase, which becomes gapless as you add more chains. So this area here, where this deltas is nothing but so-called non-local string operators, which is a lot discussed in the one-dimensional systems or quasi-1D like a ladder. Here is a disordered phase, even in it is gapped here. And if you add more chains, you can start to see this gapless extensions pops up. This is the boundary. These are just the critical lines, which meaning this becomes gapless. If you add more chains, this happens. There's an even and odd effect here. And after the chain become infinite in a 2D limit, this area becomes gapless area of the V phase that was identified. So I want to tell you that what I'm showing you here, the purpose of this slide is basically, even you have a ladder, you can have some of the disordered phase can be captured in a very small geometry. So what we were saying, okay, why don't we just look at the small ladder and see what happened? So intermediate phase under the field of ferromagnetic Kitaev, antiferromagnetic gamma, and we had a small gamma prime to get the zigzag along here. So here, this point is a Kitaev, and the other point here is the gamma interaction. So here is the ferromagnetic Kitaev, and here is the gamma, antiferro gammas. We do find that if you apply the field along the, in this case, 1, 1, 1, and then rotate along the A-axis all the way to here, and we do find that there is an intermediate phase, and these are adiabatically connected. It looked like adiabatically connected to the this pure Kitaev point. And as you rotate the angle towards the A-axis, these things drastically decrease. And polarized state appears in a much lower field. This is Kitaev, and this is a zigzag order. So there is no intermediate phase in the A-axis. There is a direct transition from zigzag to some kind of partially polarized, because the spin-spin correlator is completely not zero. It's still finite. So there is a direct transition to a partially polarized state, and we don't find the intermediate phase that has been discussed in the is kind of found in the experiment. So we said, well, at least this is telling us that this might be some intermediate phase does appear, and in this case, maybe somewhat related to the Kitaev within this confined geometry. But then we were kind of thinking that at least we can see what happens in an entire phase space. So we just look at the K gamma in an entire phase space from the phi to the all along the lines. And we have found that in addition to ferromagnetic Kitaev here, and then antiferro Kitaev here, there are disordered phase that are highly entangled. So the phase space where highly entangled disordered phase in quasi-1D system is this area, which is the antiferromagnetic gamma, and another one in here, which is near the antiferro Kitaev, above the antiferro Kitaev with the ferromagnetic gamma, and there's another one in here, which is again near the nearby the antiferro Kitaev interaction. So all other places, in fact, are all ordered. Yes, Ungu?
So how do you know they are entangled? So did you calculate some entanglement entropy or?
Yeah. So this color here is entanglement entropy. So the brighter ones has the higher entanglement. So in fact, that this one, yeah, I should explain this. I was a little bit in a hurry because I have a lot to explain, but maybe I can cut off some of them. So if you ask questions, I will slow down. In this color maps here, the first one is so when you do, this is a DMLG calculation. It's an IDMLG. And the x-axis is the phi. So I'm moving from ferro Kitaev here. It's an anti-ferro gamma, anti-ferro Kitaev, and here is the ferromagnetic gamma. These two color plots are representing, one of them is when you do the DMLG, there is a transfer matrix, and you can get the entanglement spectrum, which are nothing but the eigenvalues of those matrices. So the eigenvalue of the reduced density matrix, the largest one is called lambda 1, and those ones has a lot of information. So if you take the lambda 1 and take the second derivative of this largest eigenvalues with respect to the phi here, that's what it is, and take the log because the derivative is so large. So you take the log, and that's why we plotted, and that determines the phase boundary. So these are the phase boundary. You can see a lot of things are going on within just one parameter, well, two parameter, k over gamma, and then magnetic field is along the 1, 1, 1, which is the c-axis. Here, and then this one here is just showing the entanglement entropy. So there is ferromagnetic Kitaev, anti-ferromagnetic Kitaev, both are highly entangled, but even anti-ferro gamma is even more highly entangled. And this one is also something interesting. And that one is also, there's none of these are having a magnetic order in the quasi 1D system, which means that these are the place to look for some quantum spin liquid in the 2D system. On the other hand, those ones here, which is highly entangled, look like entangled, but these are all of the ordered state. And here is also the same thing. I'm going to show you the little bit of better data here. This is around so if you look at in here, this is so busy here. Because here, there is not much going on. Here is just Kitaev and then anti-ferro gamma, which seems like a disordered. There's a debate on this. Pure gamma model is zigzag ordered or not. It is indeed close to zigzag, but it is not zigzag ordered, at least in this latter pictures. And I think it's believed that even in 2D, it's not ordered state. But it is nearby some of the magnetic order state. So I just expand this area, zoom in, and then see what is happening around there. And what we are finding is these pictures. You can see that there are at least this place. So here is the anti-ferro Kitaev range. Here is the 0, 0 is a pure anti-ferro Kitaev. So this is disordered, SC is disordered, and UC is disordered. All of others has incommensurate magnetic order. So people have been studied like a few Kitaev here and apply the magnetic field along these directions that go up here. And they have found some collapse of the entire energy spectrum. And they claim that it is a U1 spin liquid. It is indeed has some kind of disorder state, which is this SC state. But most of this phase space, in fact, has incommensurate order, which you can miss if you had a 24-side ED calculation, because they are based on the 24-side ED. But if you add a ferromagnetic gamma interaction, which is this side, then in fact, one can stabilize all of this disorder state, which occupies much wider windows. And this 3 state, which are disorder, there's no magnetic orders, is a scalar chirality. So scalar chirality is the S cross S with the dot S. Anti-ferro Kitaev has the chirality, which is this one here. That's the chirality, which defines the anti-ferro Kitaev. This staggered chirality has a staggered pattern, which is in the middle here. However, there's a total chirality 0. So basically it moves backwards, like one is moving this way and the other is backwards and so on. So there's no total chirality, despite that this one appears in the uniform magnetic field. And around this area is also another chirality. So what I'm trying to show here is that if we are looking for some kind of exotic or some non or disordered, at least the disordered state, which are the candidate for the spin liquid, the right parameter space will be anti-ferromagnetic Kitaev in field in this area. as well as the ferromagnetic Kitaev with the antiferro gammas. But a lot of places where we have incommensurate orders can be dismissed by the, or can be disguised by some kind of disorder state because of finite size effect. So one has to be careful. So this one is giving us some kind of guidelines. Now, people have looked at this. Of course, we are not the only one. The earlier ones, very early ones, this is theory papers, has proposed that there is a C-axis. This is again 111 is the C-axis. Again, they have said that there is some kind of intermediate phase that appears, some model Hamiltonian, which is a little complicated, but that's the first one they have proposed. And after we've done this, in fact, that this people here have looked at this, in fact, the tensor network calculation. This is a huge calculation. It's pretty well done. What they have found is that, yes, indeed, there's some intermediate phase here, but apparently this is different from the Kitaev spin linkage. So instead of Kitaev spin linkage extended all the way here, they found the Kitaev spin linkage is confined in the two-dimensional system. But indeed, the one that we have found that this might be disordered, this is disordered in the latter. It is a kind of disorder. They don't find any magnetic order state. And they call it MP1, MP2, which is a nematic paramagnet, where N referring to the C3 symmetry is spontaneously broken. In the latter, we don't have C3 symmetry because it's not a honeycomb. So apparently we cannot catch any of this in the latter. But it is showing that how that can give us the guide into the phase space where we are looking for a quantum spin linkage. And Matthias Kolke here has, this is a tensor network calculation. DMLG has found something very similar. So they do find here Kitaev, and there's a huge window of disorder state that appears above the zigzag order state. But these are all C-axis. There's another papers here is also in C-axis. So theoretically, we've been struggling to find a kind of quantum disorder state in the AB plane. And I have recently found that this paper, I believe it's from Kia's group, and they have looked at something interesting. So they have looked at the Kitaev with J3 interactions, so third nearest neighbor interactions, and then put the field along different three directions. This is A-axis, B-axis, C-axis. They do find the sum of intermediate phase above the zigzag, which are stabilized by the third neighbor Heisenberg interactions. Because the Kitaev and Heisenberg interactions all isotropic, as we have expected, that this polarized state here, which you can see that the polarization occurs around this field along the C-axis, which is same as the A-axis, and that is telling us that this calculation is working basically, because I would expect that exactly the same thing. B-axis should be different, and that's exactly what they are seeing. So it's kind of interesting to check. But on the other hand, these parameters may not be quite close to the ruthenium trichloride. But I would think that this is an interesting theoretical paper to look at it and figure out what is this IP1 and IP2 in particular. Okay, so I would say that this Ising topological order under the magnetic field in the ruthenium trichloride is still a microscope. The microscopic mechanism still remains to be open. Particularly this particular systems. All right, so let's move on. So another ones that I was thinking maybe one can check is the how we can get this type of the topological transition without relying on the microscopic details. So that's where this magnetotropic coefficient came out. So as I said, if you change the magnetic field direction, the turn number changes. So when turn number changes, the system has to go from one turn number to another turn number. So that means that between these two, there has to be a topological phase transition. In the this is always true, no matter what, because the topology is changing from one to the other, and you cannot locally remove the topology. So that's why it's a topological. Topological meaning it's robust unless you cut it and then recombine it. So there has to be a transition between these two, and that has to be independent of the microscopic details. So that means if there is a transition between these two, there has to be a thermodynamic quantity. Transition between the phase with a different turn number Well, there has to be some transition between these two, and that has to be independent of details of microscopic parameter, and that should be based on the symmetry of the Hamiltonian. So whatever the Hamiltonian that I have, that Hamiltonian should have the symmetry of the lattice, time reversal symmetry, and so on. So the symmetry is just such a powerful, what do I say? The concept that it's hard to break unless you break it externally. So the idea, again, back to the Ising TIO, topological order. This is, I told you this, so I'm not going to repeat. The forbidden Ising topological order is the one that I just thinking about it. So if you, the one thing that you can think about, like Ising topological order happens in few places. It's not the Kitaev is probably, if it's a Kitaev is hard to understand. The best way to think about is a P plus IP superconductor. So P plus IP superconductor is a PX plus IPY superconductor, spinless case, has been discussed in the, for example, in the strontium to ruthenium 04. Of course, there's a spin, but if you can imagine having some kind of P plus IP superconductor, and P plus IP superconductor is fully gapped in the bulk, but because it breaks the time reversal symmetry here, one could have spontaneous supercurrent along the edges. And to have such this P plus IP, that the consequence of P plus IP is going to be an edge state on the boundary, which will have supercurrent. And this one breaks not only the time reversal, because under the time reversal, the plus I become a minus I. So these two are degenerate, but then spontaneous choose one of them, and the choice of the one of them will generate the edge state on the boundary. And not only it breaks the time reversal, but also breaks the meter, because it's a px plus IPY. So under the one of the meter, if I change a px to a minus px, this is again degenerate, and then they have to spontaneously break the meter to get the edge state. So this order requires the both time reversal and meter symmetry breaking. So now under the magnetic field, we automatically externally break the time reversal. So that's why Kitaev under the magnetic field allows to have this non-abelian anion, which are described by Ising topological order. But under certain magnetic field, in fact, that it does not break this meter. In the lattice of this spin model, is nothing but one of those C2 symmetry, which some people call the pseudo-meter symmetry. So if you have an angle, which is in-plane angle, you can see something like here. If you have this honeycomb structure here, C2, which is a 180 rotation along this axis, for example, and you can rotate along that directions or along these directions. If you have R3 bar structures, so you have 3 meters in a plane, meter planes, 3 meter planes. If you have a different lattice, then you can externally break the meter, then you're left with only 1 meter. So in the R3 bar, this phi is the angle from the, let's say, A axis, which is this is the bond between the ruthenium to ruthenium. So A axis is going to be perpendicular to here along the B axis. And if I choose the angle from the A axis, you will have this meter, which appears 30 degree, 90 degree, and 120, and so on. So there is a 60 degree, and there are 3 of those will appear, and those special direction under the magnetic field is not going to break a meter. That means that that particular direction of field is going to be different from the other directions. So these are the some of the special directions. So non-existence of this Ising topological along the C-axis is in fact valid in general spin model. As I said, all of those interactions, you can add anything you want to, as long as they are allowed by the symmetry of the lattice. This is a C2 axis. You can see the SX changes minus SY and so on and so forth. Apply all of this back in here. Whole Hamiltonian is invariant under the C2 axis. So these are the B axis. So B axis is special. As I said, if you had all 3 bar, which meaning that you have C3 symmetry as well as 3 C2. If you have monoclinic samples, then there's only 1 C2 left, which is also give us the KX Kitaev interaction is not isotropic. It's a KX is equal to KY, but KZ, which is a Z component of the interaction, is different. It's the same for the gamma. Gamma X, gamma Y are equal, but gamma Z will be different. Heisenberg is isotropic to begin with. It doesn't matter. So this is the B axis along the phi. And so that means that if I apply the field, I put the in-plane field and rotate them in plane. So if you rotate in a plane, then what's going to happen is that as the field rotate and then cross the b-axis, there has to be a topological phase transition. So that has to be, that's consistent with this sign change of the half quantized thermal Hall. And we are saying that if that's the case, we should see the exactly same thing in this field-driven or in-plane-driven kind of the transitions. Now the question is how we can detect it. So that means that there is a free energy, which is function of in-plane magnetic field angle, and we have to see the derivative of the free energy to detect this transition. So in fact, that we know what that is. Free energy derivative of this in-plane, the field angle is the torque. So first derivative is a torque, and you can see that torque does unfortunately go to 0 along this b-axis. So here is a plus A, there is a minus A, and in fact the torque itself goes to 0. So when it itself goes to 0, it's hard to tell the singularities. But if you take the second derivative, which is this kappa is a self-energy, the second derivative of the free energy, in fact that they will start to see this singularities. If I take a third derivative, this will jump. So because the slope is going to be negative and positive, so there will be a jump in the third derivative of the free energy. Question is how we detect such a thing, and that's exactly the so-called magnetotropic coefficient. So second derivative of free energy with respect to the field angle is the magnetotropic coefficient, and we are saying that the signature of the no Ising topological order appears along the b-axis should be detected by the magnetotropic coefficient. So this is not, it's a very new technique. It was developed around the, not long ago. So I believe it was around so a couple of years ago. So if you look at the free energy, the first derivative with respect to the field is a magnetization. Okay? And then first derivative with respect to the angle is the torque. So this we know very well, and kappa is also very well. Like a second derivative of field strength is the susceptibility. And if you take the second derivative of field with respect to angle, that's the magnetotropic coefficient. And how you measure is rather interesting because one can look at the resonance frequency shift, and I'll show you what that is. So how you do this is that you can go to the, you put samples on some silicon cantilevers. And so here's an energy, and those energy is written in terms of the angle of the rotation of the sample with respect to the magnetic field. So these are the delta, the theta, and K is the cantilever original, the spring constant, K here. But if you put the samples, this will deviate from this silicon cantilever, which is the tau is the torque, with deviation from here is a delta theta, and K is a magnetotropic coefficient, which is the second derivative. So one just have to solve this equation, and once you solve it, you will end up with that this resonance shift from the original without the sample. So this is the shift due to the sample mounted on the cantilever is going to be proportional to the magnetotropic coefficient. So basically they have to measure the shift of the frequency without the field, like a B equals 0 is a magnetic field, no magnetic field. So they put the samples and then no magnetic field, there'll be some resonance, and then put the samples and then put a finite field. The shift of here is going to be the one that measures the second derivative of the free energy with respect to the magnetic field angle. So this was tested, in fact, interestingly, tested on the ruthenium trichloride in 2018. The field angle they have used was not in plane, they used the outer plane. So this is 111, which is a c-axis versus the b-axis. So they rotate along this theta here, not with a phi here, but in any case, well, actually they are not along the b-axis, it's just some arbitrary angle in the in-plane. So by changing the thetas, they do see this cusp here. These are the magnetotropic coefficient is singular, and that marks the yield temperature, where the zigzag magnetic order disappears. So this is more of in plane, and this is out of plane. So out of plane requires much higher field to destroy the zigzag order, but even that, it doesn't saturate. So in plane magnetic field, that has to be done, and they are going to put the samples and do the experiment. In fact, they had some of those data, but they were not very confident about it. So they are going to redo the data, the experiment, and we'll see what happens. So that's the, up to here is a ruthenium trichloride. So probably it's a place where I can stop and get some questions before I open up something new. Maybe I got it too fast, or okay. If there is no questions, then probably I'll just move on. So I'm going to look at the slightly, move to slightly different directions now. That is the higher spin Kitaev model. So, well, the tuning criteria, I think we still have to wait and what is going to happen in the experiment as well as theory, because as I said, I think we are still looking into the microscopic details, or not a detail, it's the important details of the theory we are still missing, as well as experiment has to be reproduced and so on. So let's look at the different spins. I was thinking that, well, maybe one can have something like a higher spin Kitaev. So what happens if I have higher spin Kitaev? And I was not the only one, you know, a lot of these ideas are shared. So apparently other people are also thinking about it too. If I have a spin 1 Kitaev model have this peculiar properties where you can define so-called Plaquet operators, and they commute with Hamiltonian. And that happens with any spin, in fact. So maybe that you know, different spins might have quantum spin linkage, and they might have some Majorana extensions. Maybe there might be some half integer or integer spins are different, just like Heisenberg model on chains or ladders. You can have Haldane gap or not, depending on the half integer or integer spins. So all of these are interesting questions. And in fact, that they were kind of studied back quite early in which I didn't know until very late. But Bhaskaran here and these people have looked at the spin large S Kitaev model, and they do find that in some of those features that I have discussed. However, the spin 1 Kitaev model is not solvable. So as I said, the Plaquet operator commute with Hamiltonian, that defines the spin-spin correlator is short-ranged. However, because it's not exactly solvable, people have done the numerics on it. So this reference 2 and 3 are the different numerical calculations, and they have found that maybe this entropy as a function of the temperature, this is high temperature expansion calculations, they found that the entropy at a certain temperature will have half of the log of the 3. So there's a half plateau here before it reaches the full entropy of log of the 3. And so that was indicative that there is interesting physics going on even in the spin 1 systems. Okay. And this one is have said that maybe spin 1 also gapless spin linkage. So that was this data here, Natsu et al. There they have looked at again, it's some numerical calculation of the finite size. They change the system size and see how the gap decreases as a function of number of the system size. So they do see that gap goes down. Okay, so that was nice. So the question is, how do we get the spin 1 Kitaev interaction? So I give you the kind of details in the first lecture, how you can get the bone-dependent interaction, and that requires the few conditions. So a lot of them is Spinové couplings and Spinové coupling, large interactions, and you need to have a right filling and the Hund's couplings. So now we want to get the spin 1. So how do we get the spin 1 Kitaev interactions? So to get the spin 1, electron is not a spin 1, it's a spin half. However, if you put them in this crystal field, we know that due to the Hund's coupling here, So if I have a D8, so let's say this is a transition metal surrounded by octahedra, D8, and I have crystal field splitting due to the crystal, this octahedra, and T2Z is just splitted as we discussed earlier. Now, if I have a D8, I will completely fill the T2Z, and then Hund's coupling will make my ground state will have easy to be aligned with above. So that forms the spin 1 state. So spin 1 state with above, and so this is total S equal 1 and S equal 0, S equal minus 1. So the condition is that the crystal field splitting, which is this crystal field splitting, is larger than the Hund's coupling. And this Hund's coupling has to be much bigger than the Spinover coupling of these transition metals. So we don't have mixture of the different spins because to get the bond-dependent interactions, remember that I had to use XZ orbitals, hopping in here with XY orbitals with above. And if you write in the pseudo spin, that is a spin flip process. And that spin flip process is allowed between this bond because it's XY overlap with XZ. And on the other hand, XY doesn't overlap with XYZ here, and so on and so forth. So we didn't need the mixture of the different spins with the different orbital. But if I start with the spin 1, due to the low Spinover couplings, we don't have such a mixtures. But on the other hand, we could be using another path, which is basically this anions. If you use this is cation anions. So if I use a Spinover coupling in anions, so this one is forming due to the Hund's coupling spin 1 state, but this anions, which will be fully occupied, it's a P6 state, but due to strong heavy anion here, heavy atoms, p orbitals are splitted by half and 3/2. This is a real L, not an effective L. So we'll have 3/2 and half, which are splitted by lambda p. So here's an atomic Spinover coupling of the p orbitals, which are kind of large. I mean, depending on which one we are looking at it, but if you go down there, down in the periodic table, it's about 700 MeV or and so on. So they are not small. If you use a Spinover coupling anion, then we may be able to generate the bond-dependent interaction. So this process this is an idea, and how we work it out is not that, I mean, one can do it, but it's a kind of lots of calculations. So remember that we take only one bond, so we can just look at one of this bond and then apply some of this using a symmetries. Here, this orbitals in the transition metal is an easy orbital. So we are looking at a dx square minus y square, and then d3r square minus z square. So is that supposed to be r square? It's just z square minus r square, right? So in any case, so we have this two easy orbitals here on the transition metal side, and this the octahedra made out of p orbitals. I have made it slightly separated here just for clarity. They are not separated. They are just put them together, but I have to put at least 3 different orbitals in this p orbital positions. So if we have those p orbitals, so px, py, pz, and they have different energy scale due to the Spinover couplings in these positions, there are different hoppings. There's a T1, T2, T3 because this is easy orbitals overlap with px and py and pz are slightly different. However, if you put in the cubic symmetry, they are related by some ratios here. So these are just some Slater-Koster type of the calculation, which tell you that how they are related by certain symmetry, give you the numbers. So in fact, there's only one parameter, which is a TPD sigma. So go through this hopping process, as well as I said, that you have to have on-site interaction. So we start with on-site interaction and do the second order perturbation theory, just like what we did for the J effective half. Here we have lots of on-site interaction because we have 2 electron on the transition metal. So there could be no holes, there'll be a 0 holes, which is 2 electrons there, but I can move 1 electron in the other side. So there could be 1 holes, 2 holes, and so on. So this is, in fact, and there could be also 3 holes, depending on how you move back and forth. It's a bookkeeping process, and one has to be careful doing these calculations. In any case, one can do it, and that's what my student has done it. The path that one has to take is at least 3 different kind. Here is an M1 transition metal going through anion through the rigging type of the exchange pass. One can do it exchange pass like 1 and 2 and then 3 and 4. This is moving that way and then back going this way. It's just a different order. And there could be also going only using a one of anion and leave the other anion intact, and then there'll be another process backwards. So all of this has to be taken into account, and we keep up to the fourth order perturbations. Then what we end up, I'll just give you the answer. So what we have found is that the indirect, which is going through the p orbital, the superexchange path using the cubic symmetry in the limit that the Spinover coupling in the p orbital is larger than the Hund's coupling in the p orbitals, then we always end up with this exact ratio. So Kitaev interaction here is twice bigger in terms of magnitude, twice bigger than the indirect Heisenberg interactions. And this one is proportional to lambda p to the squares up to the fourth order perturbations. The indirect interactions are generally ferromagnetic, and which you may have seen it in the case of good enough and so on textbooks, what people say that when you have 90-degree shared p orbitals, the superexchange give you the ferromagnetic interaction. So this comes out to be a ferromagnetic. That means the Kitaev interaction is actually anti-ferromagnetic. In addition to that, of course, we have direct hopping. Direct hopping is going to give us the Heisenberg interaction. That's it. So gamma is up to the fourth order is exactly 0. And to get the finite gamma, one has to make a much higher hopping. That makes sense because spin 1 has a 2 electrons. So if I want a gamma is that you have to flip the 2 spins. Remember, it comes as S press. So I have to flip the both up or down, connect to the down. That means that if I have to flip the spin 1 to a spin 0, S equals 0, I have to use 2 electrons into the flip it, and processing that requires more than the fourth order to get to be finite. So if I combine the both, in fact, this is what we have, the total Hamiltonian with bond-dependent. Kitaev interaction here is in fact bigger than the indirect Heisenberg interaction. And it's even better because this interaction here is a ferromagnetic. On the other hand, direct exchange is always anti-ferromagnetic. So this J, which is a total, in fact, that they not exactly cancel out, but they reduce each other. So this Heisenberg interaction is in fact smaller than the anti-ferromagnetic Kitaev interactions. So one can generate the spin 1 Kitaev interaction through the anionic Spinover coupling in the p orbitals. So what about the spin liquid? Well, okay, so we've done this ED calculations for a spin 1 Heisenberg Kitaev model. Because it's a spin 1, we are even more limited now. Instead of 24 site, we can have 12 or an 18 site and try to see if there is a disordered area. And indeed, we do find, so this is the, one of them is 18 site and the other is a 12 site. The red color is the second derivative of the ground state energy. This is just the ground state energy. If you just look at the solid red, it's an 18 site second derivative. We do find that there is some disordered state, and anti-ferro Heisenberg will stabilize anti-ferro interaction, anti-ferromagnetic magnet, which is just like a spin half. And ferromagnetic Heisenberg will stabilize the zigzag. So this is just like a spin of half. So that's how we have found that there could be interesting spin liquid even in the spin 1 model. Now, the question is, okay, real material. So we've kind of, this is suggested. Of course, all of this has to be tested. So one can find honeycomb in the honeycomb or the triangle lattice in the van der Waals materials. So lots of this transition metal dye in this case is dihalide you can find dihalide or dichalcogenide. They do have layered structures. This comes with a triangle. It's a nickel diiodide. It's a spin 1, but it's a triangle lattice. It has helical orders. People have been representing or explaining them using J1, J2, J3. So most of those van der Waals materials so far has been explained by further neighbor Heisenberg interactions like a J1, J2, J3. And such a bone-dependent interaction has not been even mentioned, but I think that probably a time to revisit these materials and see if such an exchange might be a better description than extended Heisenberg models. Chromium triiodide is also something interesting. It's D3, so it's not a D2, it's a spin 3/2 honeycomb. Chromium is surrounded by iodide here. There has been some debate over these materials because the chromium triiodide bulk is ferromagnet. If you make 2 layers, the layers make antiferro alignment. So depending on how layers are formed, one can make the ferromagnet and antiferrous between the layers. Single layer was made, and single layer was ferromagnetic with TC of about 40, something around the mid 40 Kelvin. So it's a very high TC. That means that it's not an Heisenberg model, because if you have Heisenberg, pure Heisenberg model, Momin-Wagner theorem tell us if you have a purely a 2D system, there's no finite TC. So this has been a kind of debate over the recent years that maybe this has the Ising anisotropy, and those Ising anisotropy has to require some spin-over coupling and then trigonal distortion, or maybe it's described by XXZ model. So this is one of the, I think this is a poster group has described this as some kind of XXZ models which are coming from spin-over coupling of anions. These people here, MPJ papers, have suggested that there is a large Kitaev interactions. This one here is an Ohio group, also have suggested that there is a large Kitaev interactions. So where it is still, I think it's an interesting question. There will be a small workshops going on, months to pin down what is the magnetic interactions in this compound. So that's another interesting ones. Yes, Sungu?
So these materials have a higher TC. So do you expect we need to apply strong magnetic field to kill this ordering, as in alpha-leucine chloride, to achieve a Kitaev spin liquid or any kind of spin liquid?
I think this, okay, so if you ask, so first of all, so based on our calculation, which we are holding because we have to understand what's going on in this material. What we found that in fact the Kitaev interaction is not large. I actually thought that it's large as well. So I remember that I gave a talk on some of this, and I sort of said that it could be hard, or it could be large, or it looks like it's large. But after doing this requires a lot of calculation, by the way. It's the state that you are going through, the excited state, is incredibly many. So one can easily make a mistake. But in any case, at the moment, we feel that when you say large, meaning there is an Heisenberg interaction, and Heisenberg interaction is larger than the Kitaev interaction. So if that's the case, I would think that it's hard to get the spin liquid in this particular material. But if you talk to other people's here, for example, they might have different opinions. Yeah, at least from my side, it's probably harder. So we are still looking for how to generalize this. I like the fact that the spin 1 has antiferromagnetic Kitaev interaction, because as you may know that if you apply the field in the antiferro Kitaev, you come to the Yuan spin liquid, propose the Yuan spin liquid, and there are not many examples of Yuan spin liquid. I don't know any, in fact, confirmed. So that will be really exciting if one can get the spin 1 Kitaev materials. Yeah, so, and I have a sense that this might be a better place to go, but one has to tune it in such a way that we have to generate into the honeycomb structure. And there are transition metal oxide as well. Did I answer your question?
Yeah.
Can I ask you some very naive question?
Yes.
What is main motivation to look at or study this higher spin Kitaev model? Usually, according to general wisdom, if you have a higher spin, you tend to have more ordered state rather than frustrated state.
Yeah.
So to find it, the chance to find any spin liquid state out of this higher spin Kitaev model, I think the chance is much less than spin 1/2 state. So then what is the behind the motivation to look for this higher spin state?
Right. So yes. So in principle, I think there are more than one reasons. So in principle, you are right that if I have a larger spin, because I'm moving towards more classical spin, the tendency to have a disordered or quantum spin liquid is less likely. However, in the Kitaev or even a gamma interactions, those are highly frustrated in such a way that it was shown if you have up to spin 1 or spin 3/2 is a somewhere marginal, that one can still have a classically very, very disordered state. So we know that from some of the theoretical studies, the spin 1 Kitaev, especially with the Kitaev interaction, is disordered. And numerical calculation also suggests, I show you very small size, but there are other people who have done different studies, and they do find that Kitaev is likely disordered. And another question that one can, so that's one thing. So it's basically it's due to the Kitaev interactions, not other interactions. These interactions are very frustrated that even larger spins can still were able to find a way to have a quantum spin liquid. That's one thing. Another thing is that as you see from ruthenium trichloride, as well as the iridium oxide, those honeycomb iridate, they all comes with, we think, they all comes with the ferromagnetic Kitaev interactions. And many of us are kind of making a consensus that this might be just mainly a ferromagnetic Kitaev interactions. Ferromagnetic Kitaev interactions, if you put a field, they almost completely polarizes. It's hard to, the reason that we are getting all of this intermediate state is not a physics of Kitaev, it is a physics of gamma interactions, because that's why if you're aligned along the AB plane, they are kind of gone. So these ones here along the C-axis is coming because of gamma interactions. So I believe all of these are connected to the finite gamma equal 1 here. So Kitaev here, ferromagnetic Kitaev is kind of like a 0.08 Kitaev interaction. So that's like a 2 Tesla. It's polarized. So that's why it's puzzled why the ruthenium chloride 3 is seeing intermediate state, because once you put in that ferromagnetic Kitaev without the gamma interaction, it's hard to even get any intermediate state because you will immediately polarize. So that's coming from there. On the other hand, if it is an antiferro Kitaev interactions, which I don't have slide, but people have shown that the antiferro Kitaev, because it's antiferro, this sign here, antiferro Kitaev case for a spin-off, they have a much robust window of the Kitaev spin liquid. So if I had antiferro-Kitaev and putting a field, I will get the non-abelian anions. If this spin 1 was also described by the non-abelian anion. We don't know if that's the case because it's not exactly solvable. But if that's the case, you will have a much robust or rigid window of the non-abelian anion state. That's another motivation to, that's why we've been looking for antiferro-Kitaev. There are people have been trying to find how you can, kind of tune it around to have an antiferro-Kitaev even for a spin half. Spin 1, in this case, naturally gives us the antiferro-Kitaev. And under the field, it goes not only a robust window of the Kitaev phase, but also there is a gapless, there is some gapless Yuan spin liquid, which is numerical evidence has been shown that requires antiferro-Kitaev as well. So there are at least 3 reasons why we've been looking for spin 1 Kitaev.
Okay, then at the end, suppose you find some spin liquid state which produce fractionalized quasi-particle. Do you think or do you expect this fractionalized quasi-particle is just another Majorana fermion, or it can be something else?
Yeah, it can be something else. We don't quite know. So that's the motivation here. Basically, yeah, so that's an open question. We don't know if that's Majorana excitations or something else. At the moment, at least we do know that it looks disordered. We also know that if you apply the field, we do have some gapless excited, the gapless state that appears in the middle. There's an intermediate phase in field. So that much has been known in the, well, actually it's more than that. I know that Yongbek has done some study with people in Korea. So some of you may know more than I do here, which is not my work. They have shown that, yeah, they have shown that the excitations there is something non-trivial, but I don't recall what was it. So we know that it may not be a Majorana excitations, but maybe it is. I don't know.
All right, thank you.
Okay, so let's move on. So that's it's a very early stage of the spin 1, and we are still looking for how to understand this, well, how to get into the spin 1 materials. So this is, none of this has been studied, and yeah, I mean, I think it's a very early stage. Even Ruthenian criteria, when we were talking about, it took a couple of years to get people get to know. So we'll see how this goes. So requires the further studies. Then we'll move to quite different topics. So I'm out of Kitaev now. So if you have any questions about the Kitaev, please go ahead. Yes, Sungo.
So your magnetotropic result.
Yeah.
I think you only studied the in-plane.
Yes.
Yeah. I think even out of plane. So I presume your result based on the gaplessness of C Majorana fermion.
Yes.
So then out of plane, you also see some signature.
Yes, if you have ideal crystal.
Mm.
Yeah, so if you have an ideal crystal, that's the case. Because when Kitaev was writing those interactions, he doesn't have, he has honeycombs, but he's writing everything in terms of those ideal case. In reality, if the crystal breaks those mirror symmetry because of those monoclinic distortion or trigonal distortions, and layers are stacked as well. So I think those directions might be much more, it's kind of, because the mirror symmetry is externally broken, so you're always allowed to have a gap. So that singularity will be smeared out. So I think the best place will be B-axis, where monoclinic has 1 meter there, pseudo mirror symmetry there.
Yeah, so right, maybe yeah, maybe we can, I can, I have some more comment, but I want to discuss with you more later.
Okay, yeah, so we can probably discuss later.
Yeah.
So I think I have only a few minutes, but let's see if I can cover this interesting material. So
You can have 10 minutes or 15 minutes more. Don't worry.
okay. Okay, so I think that will be enough then, like 15 minutes, 10 or 15 will be enough for this interesting, the tantalum disulfide. So let's just remind you that we are interested in designing a multi-insulator, and remember the multi-insulator where Hubbard interaction is larger than the bandwidth. So to get that, one way to get it, of course, one can increase the Hubbard interaction, but that's kind of given by the nature, so it's hard to design it or hard to engineer. But on the other hand, we can change the bandwidth. So that's basically an idea of twisted bilayer graphene, because by twisting the bilayer, the graphenes, and putting together and twisted it, you can generate the flat band. So when it's a flat band, T is reduced, not the U, and we end up with the corollary physics. So that's how you would generate the corollary physics. Ruthenium trichloride is also similar, because remember that I show you that the band appears to be rather flat, and that's the place where you can begin that, okay, something non-trivial might happen in this case. So tantalum disulfur is one of the candidate of the quantum spin liquid, and I'll show you why that is the case. And we are not seeing a quantum spin liquid, but on the other hand, there's some interesting things that I think it requires the further studies. So we are trying to engineer the K-Millet-Hubbard model out of flat band in the tantalum disulfur. So I'll give you a little bit of introductions about the transition metal dichalcogenide. So all of these materials coming from molybdenum or tungstens, disulfur or diselenide, all of this has a filled shells. So you go to the periodic table, they have kind of semiconductor behavior. Some of this has this type 2 vials and so on. So they have their own very interesting band topologies. But they have filled shells. And on the other hand, tantalum disulfur is rather unique in a sense that it has partially filled. So there's a 1 electron in a unit cell. It makes the structure like a triangle here. So these are the tantalum, 5D, and then sulfur is sitting and making a nice triangular lattice. They come with the different structures. It's 1T tantalum disulfur is the one that I'm going to talk about. So tantalum disulfur, as it is large, it is a metallic, band structure shows that it is metallic, has a large dispersion like that. But on the other hand, as you cool down, what happens is that this goes through the several phase transitions. So this was 600 kelvins, they go through so-called incommensurate charge density wave, nearly commensurate charge density wave, and then there's a charge density wave where this is the resistivity in the log scale. As a function of temperature, it jumps and then it becomes insulating behaviors. So, and if you pressurize these samples, a certain pressure, it becomes a superconductor. So many of those transition metal dichalcogenide, those things become a superconductor under pressure. And some of them might have more than some interesting physics. And I don't think it has been explored that much yet. So it might be interesting to think about. So if you look at the low temperature here, the charge density wave, a commensurate charge density wave, incommensurate, nearly commensurate charge density wave, that commensurate charge density wave comes with a structural transition. So what happened is that these are all tantalums, and 13 of tantalums, put them nearby and then separate into each other and form a Devi star. So these are the 13 tantalum making a Devi star. And this is the kind of structural transition that comes together with the charge density wave. But given that it's a 13 tantalum, and each tantalum give you 1 electron here, 1 electron has it. So it's odd number still. So you still have 1 electron in the new unit cell. What's interesting, once you put them this Devi star, remember that without this Devi star, so in a very high energy or high temperature, before this commensurate charge density wave occurs, it has a quite dispersing band. But once it becomes Devi star, we end up with an extremely flat band. So this is an ab initio calculation done by the Dr. Jin. You see the nice flat band. The bandwidth is really tiny. It's like less than 20 MeV. And it's a 5D material, so electron, the Coulomb interaction is probably at least something like about an EV here. So it's ab initio calculation show that it's a half filled metal, and charge distribution on a flat band is shown in here. On the other hand, in the experiment, it's an insulator. As I show you, that resistivity shoots up, actually. It's getting much, much bigger as the charge density wave formed in. So that already tells us that, oh, this is correlation effect is rather interesting. So based on that, there have been people who have suggested that tantalum disulfide with Devi star forms, that should be a quantum spin liquid. So we are not going to discuss of that part, but I think that what's interesting here is that one can probably engineer this honeycomb as towards the honeycomb lattice with a flat band, just like some of the twisted, it's a bilayer graphene or graphene. It's like a honeycomb lattice with a flat band. Then because it's a honeycomb lattice, instead of having 1 electron, I'll have 2 electrons because it's a 2. It's not a. It's a it's a 2 unit, two site, 2 atom in a unit cell, and one can probably generalize realize the K-Millet models with large Hubbard interactions. So the way that it was done is that because tantalum is making this Devi star, and Devi star, it's a composite, it look like 13 molecules here, and that makes the triangle lattice. So it's an initial triangle become a bigger triangle, and if you deposit potassium on a certain pattern, like put the potassium here in a periodic pattern, then this can cover up tantalum. So tantalum has 1 electron, and potassium will come in and donate to another electron. They bind, and that will just remove the 1 electron, and effectively system become a honeycomb lattice. And the way that the potassium pops up here is the potassium is going to deposit on the top of this tantalum, 1T tantalum disulfide. So that means that the inversion along the z-axis is broken. So there will be a Rashba Spinover coupling will be induced by putting the potassium. So potassium does 2 things. One is that change the filling of the charge, and also induce some Rashba Spinover coupling as well as some kind of atomic Spinover coupling. So that was the purpose, and see if one can make the first case of the K-Millet real system, not just the model. So that was how we started. That was the motivation. So just want to remind you that K-Millet model is the first example of the topological band insulators, where Kane and Millet have shown that you have this band, and there will be a topological state. It's a topological, and then there will be a left moving this way with a downspin, right moving on this way, which is upspin. It's a quantum spin hole, and there will be a finite spin chunk number. And the way that the model was rather written in this lambda SO, which is the Spinover coupling, and the second nearest neighbor, and this is going to be a Rashba Spinover coupling. This sum has to be reasonably large to get this band insulator with the edge state here propagating. But what we are proposing is that if you put the large U here, this will be a K-Millet Hubbard model. So that's, and this model has been studied widely. I don't think there has been any realistic material that maps into the K-Millet Hubbard model, and we are thinking that we have made one. So it's important to know that where the potassium sits in. I mean, we are speculating the potassium sits on the center of this Devi star covering up, and so that this 1 extra electron is gone, and then we end up with a honeycomb lattice. So this calculation was again done by Dr. Jin, and he has shown that if you put the potassium, the binding energy on the potassium is the best in this center of the center of the Debye star. So this is H1, is this position here, and that reference is 0. Everything else is positive. And so that in interaction, the binding energy is much better on this position. So that's where we are gonna, the potassium is gonna sit on. And if that's the case, this is an effective lattice. So effective lattice here is going to be made out of this nice honeycombs. So that's the proposal, and that's what they have made. So that's another calculation. Okay, so before we show you the experimental system, this is a partial density of state, just to show that those tantalums here are made of the d orbitals. I thought that was one of the easy orbitals, the z squares. So it's kind of rather localized within this molecule, but there will be some hopping process going around. But because it's rather localized, the bandwidth is very, very small. Despite that, there is a hopping, and that generated the topology of the band. So once we put the potassium, so this the potassium is deposited or absorbed on this site. Then what happened is that these are the tantalum Debye star, which is making a honeycomb. So these are the honeycomb lattice. Now the unit cell is going to be triple. So instead of 13, we have 39 by 39. So it's a square root of 39. So it's a 39 atom in a unit cell. And 2 electrons are from a tantalum d orbital, the outer shells. And you can see those again put the flat band. This is a potassium coming from the donating into the electrons. Because when potassium coming in, the potassium will be potassium plus, and that electron, extra electron, bind with the tantalum 5D1 here, and then put it into this position here. But you can see that this flat band making 2 band, which is the K-Miller band. So that's what we are going to show here. So here is again the ab initio calculation. You can see that these are still metal because it's an ab initio calculation. We haven't put the U here. Interaction is not added. So here it's hard to see because the gap is so tiny, as well as the bandwidth is so tiny here. But trust me that these red ones are DFT calculations, and this blue ones are tight binding fitting, and this red ones are 2 band here, and then this one is also 2 band because you have time reversal. But because of the Brashba-Spinover coupling that induced the splitting of the band when they are not in the trim point, which is time reversal in there, and the momentum, which is gamma and m point. Other than these 2 points, they can be in principle split here, but there is a direct gap in everywhere at the half field. Okay, so there is a direct gap everywhere in the half field. And if you do the DMFT, dynamical mean field theory, this was done by Arago at IBS, and she has shown that indeed, if you put the interaction U, you can split this direct band and further away, and this will be a paramagnetic mode insulator with 2 band showing up in the up and down. So this will be a upper Hubbard band, and this will be a lower Hubbard band, and that's what we think this system is going to have. And that's tight binding fitting, T Rashba-Spinover coupling, and then Spinover coupling, the second nearest neighbor Spinover coupling along the z-axis. That's the number parameters. And within number parameters, indeed, this one will have the finite spin jump number. So that's what is done. And this is the experimental data done by the Jinwon Lee at postdoc. So the first part here is the STM tomography. So you can see the nice structure of the honeycomb of the tantalum. These things, bright spots here are going to be a potassiums. And here is a DIDV, local electronic structure in a different bias voltage, like minus 450 MeV, which is this bar here, along this bar here. You can tell depending on which position where the current goes in, DIDV is going to show this one is coming from potassium site here, deposit site, and hexagons are, this red is coming from the tantalum. So there is a band gap here, which is about 200, something like nearly a 200 MeV, which is consistent with the DMFT calculation. There's no magnetic ordering, which is hard to tell because it's a films, but we think that most likely there is no magnetic moment. You can see that the large peaks, which we think it's probably Hubbard, upper Hubbard band, and then this will be a lower Hubbard band, which are mainly coming from red, and red are the tantalum d orbitals. So these are nice indication that this kind of engineered K-Millet Hubbard models. Of course, we have to have a further experimental checks to make sure that these are the topological multi-insulator, because so far we have the multi-insulator. To make it topological, one has to check the finite spin-churn number, but finite spin-churn number requires you either apply a small magnetic field and get rid of one of the edge state, then you will have a finite hole conductivity. So that's one way to check. Another way to do it is that, in fact, this is a prediction that we are making. If you put the system near the ferromagnet, the system has a very strong instability towards the ferromagnetic state. Then this K-Millet band will split into two copies of the K-Millet band. There is a gap here, by the way, it's just so small. Then each of those will be a copy of the K-Millet Hubbard band. So this will have a spin-churn number, well, the churn number 1 and -1, and the other will have -1 and 1. These two are the potassium band, by the way. So within this tantalum, you will have 1 -1 - and 1. So if I have the system either 1/4 or 3/4 field, in other words, if you were able to fill it here, once the chemical potential coming in here, there'll be a direct gap here. So that means that interaction will play the role, and then they will split further. And we think that there will be a finite quantized hole conductivity will show up. And similarly for the 3/4. I think the 3/4 is better than the 1/4 because 1/4 mixes with the potassium here, but 3/4 is kind of free from rest of them. So once the chemical potential comes all the way here, the Hubbard interaction plays some role to split them here, and then there will be a finite quantized hole conductivity. So we are looking to check if that can be found in future experimental situations. So I think I am done. This is the last slide that I have. So my summary is that the van der Waals materials, ruthenium trichloride is one of the van der Waals material, has known to be a semiconductor arranged into the transition metal halide or chalcogenide, this halide here. So a lot of this has been, I mean, we have studied a lot of oxide, but many of these others has not been well explored. I think it's time to go back and check the correlation effect in addition to those band topologies. So correlated van der Waals material is the place where we can look for Kitaev spin liquid, as well as we can also, if the nature does not provide the one that we want, we can engineer towards the correlated phase, just like a potassium observed tantalum disulfur. So I think that's the way to go. For the future directions, as I have been collaborating, I think that the one probably better to have collaborations rather than working a person. It would be nice to have material person. I think one example that I show, like a tantalum disulfur, is the best, one of the best examples where we had a material made at the Sang-uk's lab, and we have experimentalists coming in, and some of the theory, like Ara and Dr. Jin, has been the great team, and that has made some of the progress. This is probably one of the examples that we might want to see more often in the APCTP and also other places. And I am very willing and also eager and also very enthusiastic to find some collaborator at the APCTP. So, and to see that if you can discover the new materials, some microscopic theories for anions. And another interesting idea is that okay, you have an anions, how you braid them, because we have saying that, okay, this Majorana so charge neutral, and somehow you have to capture and then braid with another anions. How we do that is another excellent direction to think about. Of course, we are still looking for some theoretical experimental new method, like a magnetotropic coefficient is one of the very recent experimental method developed just a couple of years ago. Theoretically, a lot of numerical method is kind of under the development, and I strongly encourage people to spend some time to looking at these directions as well. So with that, I would like to thank you for your attention, and I will leave my last slide with my wonderful collaborators here, which I showed you in the beginning, but just those who have come for the second talk, then I just want to leave this to acknowledge my collaborator and some of my colleagues who has given me an incredible insight into this journey. Okay, so thank you.
Okay, great. So session is open to question and comment. We are behind the schedule only by 70 minutes. So please ask any question. If you don't ask a question, I may.
Yeah,
point.
so Hyun.
Okay.
I have a question in your calculation of the Kitaev interaction in S1 system in the maybe DA system. You consider the only easy orbital, right?
Right.
You neglect of the T2 orbital.
Right.
But in my sense, the hopping in this is edge here, and the bond angle is 90 degree. PD sigma, the hopping from easy to easy is almost zero because the easy 90 degree case is always PD sigma different bond of PD sigma is the mediate orbital is always also normal, right? Almost zero.
TD sigma here?
Yeah.
No, this is quite large.
But my point is each G square to px or but the nearest side the nearest G square is PD sigma with Py. One is px. This is also normal. It's almost zero.
So there is yes. So if you start from here, for example, so this is 3G squares, and this one will only couple to PZ here.
Yeah. This is this orbital is almost also normal. But
this
you
one
think about the T2 orbital.
No, I think let me just finish here. So this hopping is finite.
Yeah.
Right.
But
this hopping
orbital can hop the other side.
Exactly. The point is that they do hop. The reason is that because this guy here, this PZ, in this anions here is not the right eigenstate that you're hoping. So because these guys are made out of here.
Because
so in other words,
you include the T2 orbital. That orbital can hop the T2 orbital. The domain hopping is T2 easy hopping, is not easy to easy. So, but even T2 orbital has a lot of energy due to the crystal field is 10 Q, but overall matrix is more larger. And in my point is two competition is very important. T2G, easy to T2G and easy to easy is a competing mechanism to super exchange in the DA system. So I think we better description of the magnetic interaction of D8 is we have to include the T2 orbital contribution. Is my point. What do you think about that? So
in some sense, yes, in principle, let's say that you are saying that, okay, I have two sites here, and you are saying I have some p orbitals here in the EZ to EZ. You can also include going to p orbital and then T to Z, right?
Yeah.
So there'll be a EZ to some p orbital and then T to Z.
And back over the T to G to EG to.
And then back to the Z to the EG, right?
Yeah, so.
Uh-huh.
Yeah,
So
yeah, this
right.
path is also, I think, negligible in the right over the 90-degree.
Yeah, so they are not negligible. And in the case of J effective half, people have taken that into account. Like you begin with T to Gs, but those T to Gs, these are partially filled, these are empty in the T5, and people do take into account easy pass and comes back. So yes, you could take that into account, and I think that that won't change the form of the Hamiltonian. It might change the strengths because it'll give only Kitaev and Heisenberg for sure, because these are already, I don't think there'll be a gamma anyway. So it's a Kitaev and Heisenberg. The question is then if you include those, so here's only a easy pass. If you include T2G pass, the question is how this Kitaev and Heisenberg terms can change. Yes.
It's my point.
That's right. Yes. So that can definitely happen, and this one will be modified. Yes. Is that okay?
Yeah. Okay.
Okay. Sakpam?
Okay, thank you very much for your 2 days talk. And my question is about the magnetotropic constant you mentioned in your talk. Is it possible to write down this constant in terms of microscopic variables? Yeah, it's the magnetotropic coefficient.
Yeah.
How would you write this down in terms of microscopic variables?
So in fact that if you do a Kitaev model, because this calculation is, again, if you have all other terms, the calculation is incredibly hard. So on the other hand, you can do it with the Kitaev term itself. So let me just show you this, for example. Oops. I think I have skipped the slide here, so that's why I skipped the slide. There are many, skip the slide here because I thought that I don't have enough time to go through. But in any case, the K here, the magnetotropic coefficient, will be proportional to mode of the mass. So you can see that immediately. This is a low energy physics, is nothing but the Majorana with a gap in the Majorana. So this is m tau z is the this gap here, and that is proportional to the magnetic field in the case of if you put the field in it. You can show the free energy is mode of the cube, and they go to the cost of the 3 pi if you have R3 bar nice structures. So they go to the 0, and one can show that torque is m mod m, so that's why it goes 0, m goes to 0. But second derivative is a mode of m. Third derivative is a sine of m, so there'll be a step function here. So magnetotropic is proportional to the mode of the Majorana gap. And that's singular.
That's very convincing answer, but I guess I was asking slightly different thing. Like, I mean, how would you write down this m in terms of like spin operators?
Oh, this Majorana gap in terms of spin operator? Oh, yes.
If not spin, at least in terms of like Majorana operators.
So in terms of Majorana operators, it's H. Remember so it'll be something like this. Do I have the 3 spin terms? Yeah, so the gap is going to be proportional to this term here in terms of spin. If you write this in terms of Majorana language, then you have 2 different terms. One term will come as, so you can write this in terms of the B Majorana X. I don't think that, do I have any of Majorana language here? I do have it somewhere here. I didn't put this because I've been hearing a lot of this Majorana representation in so many talks that I got tired of it. So I decided not to put it. But, so the spin is written in terms of the B Majorana and the C Majorana. C is the delocalized one. And so you go through here, and then Hamiltonian is written in terms of this link variable, which is the nothing but this product of the B Majoranas and then the delocalized the C Majoranas. So if you put this form of these three spin terms, SIX, SJ, Y, and SKL, L, SK, Z, then you can show using this constraint here. You can see those this is all same site. That's the constraint. And you can go through all of these Prakke operators and Hamiltonian written in terms of bilinear, and that's give you the free Majoranas. So in terms of the free Majoranas, you use that, you will find that this guys is nothing but the UI, in this case, UJK, UKL, and then you will have C Majoranas with a J and a L. So there's one term which will be bilinear in a Majorana. So it just modifies so that appear as a mass term. Another term that appears is going to be 4 Majorana terms, which Kitaev has neglected, by the way. But that term is actually important when you have non-Kitaev terms. So which is like all gamma, Heisenberg, all of those are somewhat related to the Majorana interactions. So when you have those terms, it's no longer Majorana gas. It look like at least begin to be a liquid, and then there'll be a transition into something else. So this is the one that give you the mass M, and that is written in terms of Majorana is what I wrote earlier, somewhere in that slide, somewhere. I think I missed it. Now, here. So that's here. So yeah. So that's why this M is proportional to the field in this particular case. So if you look at this carefully, you can see that the singularity is better when you have a higher field. These are the H over K of 0.028. It's singular, more singular because mass is getting bigger and bigger. Again, this physics will be broken down as soon as we go out of the Kitaev phase. I'm assuming that we are still in the Kitaev. I'm assuming that if the Matsuda's experiment is correct, this has to be seen. It's a one way to confirm his experiment. And then if that's the case, then theorists has to look for her to where this can be seen in the real microscopic parameters.
Thank you very much.
Yeah.
Okay, are there any more questions? No?
There are chats here. Well, anyway, no, this is okay.
Okay, if there's no more question, we have to close this today's lecture. But let me remind you, this lecture has been recorded by our center, and if you look at YouTube APCTP, I think you can find this recorded lecture. So please revisit whenever you like to see this lecture again. And with this, I'd like to end this lecture by Professor Kee. And in the last 2 days, Professor Kee has given us very intensive lecture about Kitaev model and its current status and the new development. And also, let me remind you, Professor Kee has recently been appointed as an APCTP fellow scholar. So we will arrange more and more activities like lecture, seminar, or physical visit with Professor Kee. So please anticipate. more activities with Professor Kee. So with this, we should thanks Professor Kee for her enthusiastic lecture in the last 2 days with big applause.